So here we have a picture of pennies. So there are 7 pennies in the picture. 1, 2, 3, 4, 5, 6, 7. Is there any question about how many pennies are there? No. Everyone will agree that there are 7 pennies. There are exactly 7 pennies. Pennies come in whole numbers. You can't have half a penny, right? So a count of pennies, you have 7 whole pennies. If we look at this gold bar, it says 10 grams on it. Is that exactly 10 grams? No, it isn't. Anything that's measured is going to have a little bit of error in it. We can't measure something exactly. We can get really, really close. We can get so close that the difference doesn't matter, but there's always some uncertainty. And so our knowledge about how much gold is actually in this 10-gram gold bar depends on how carefully, how precisely it was measured. Global warming is, a big topic. Scientists have concluded that the average global temperature has risen by 0.7 degrees Celsius since 1880. And that's based on analyzing records from thousands of temperature measuring stations around the world, averaging them together, and they come up with this number. The number is reported as 0.7 degrees for good reason. If we add a 0 or 2 zeros after the 7, that's conveying a different amount of information. That's saying that we know this number to the nearest, this is tenths, hundredths, to the nearest thousandth of a degree. That's not true. We don't. What if we use the average that got spit out of the calculator when we did all the calculations and said, well, the difference is 0.68759824. The calculator gave it to me. It must be right. No, it isn't. Because based on where those measurements came from, we can only say that it's 0.7 degrees, meaning there's some uncertainty in the 7. That's telling us it's probably between 0.6 and 0.8. If we express it this way, it implies that there's uncertainty in the last digit, that we know a lot more about this change in temperature than we actually do. The 0.7 degree temperature change is actually more of an estimate. It's not a precise number. So we use a standard way of reporting measured quantities to reflect the precision of the measurement. If we recorded this as the temperature change, it would be very misleading. It would tell people that we have more information than we actually do. So we are very careful to record our numbers in a proper method. So the uncertainty is indicated by the last reported digit. So 0.7, there's some uncertainty in the 7. So this number here, 45.872, using the scientific method of recording measurements, then the 2 has uncertainty in it. So that's an estimated digit. All the digits before the last one are certain. We're certain it's 45.87 something, and our estimate is that places a 2. So the last digit in a measurement is always an estimated number. The more digits you have, the more precise the number is. The fewer digits you have, the less precise the number is. So here we have a picture of a quarter and a ruler. And if we're going to measure the width of this quarter, so we line it up on the ruler, so one side is at the 0, and then the other side over here, and we look where that falls on the ruler. These are millimeters, so this is 20 millimeters, that's 30. So this is 24 millimeters. It's more than 24 millimeters, but it's less than 25 millimeters. Can we say exactly where between those two lines it is? No. But we can estimate. We can look at that and say, well, it looks like it's a little more than halfway. So we estimate and we say the width of the quarter is 24.6 millimeters. The 0.6 is estimated, but it's important because it gives us information. 24.6 tells me what sort of ruler was used to measure this. If we just said 24, then the 4 would be an estimate, and I'd say, well, it's between 23 and 25, right? That's much less precise. Any questions about this estimated digit? We'll get some practice with this in lab. So let's look at a balance. Here's a copper sulfate on a balance, and I actually have one like this in my kitchen. So, the heavier this thing is, the farther down this black line goes. So let's look at the blown up version here so we can see it more clearly. We're not going to use ounces because we're in chemistry, so we're going to look at the grams. So we look at the scale here, and here's 0 up there and 10, and there's 10 divisions in between. So each of those lines must be 1 gram. Okay with that? So each of them is 1 gram, and the measurement line here is between the 1 and the 2. So we know that this sample is more than 1 gram and less than 2 grams. There's no uncertainty about that. It's 1 point something. But we're going to estimate, just eyeballing between these two lines, how far do we think that line is? And there may be some different opinions. Some people might say, well, it's 1.2. Some people might say, well, I think that's 1.3. That's okay. It's an estimate. You can have your own opinion. But we're going to record that measurement as 1.2 grams because the 0.2 is estimated. The way this works is you look at the measuring instrument and you ask yourself, well, what does each of these smallest lines represent? Each of them represents 1 gram. Then I'm going to estimate the next decimal place, wherever that is. I'll estimate a number there. Let's look at another one. So here's measuring the mass of a pistachio on a different type of a balance. So here we're looking at where does this line fall. Here's 1 gram and there's 2 grams. So each of these smallest divisions represents what? 0.1, right? We've taken 1 gram and divided it into tenths. So each line represents 0.1 gram. So we can see that we've got 1.12. It's between 1.2 and 1.3. 1.2 something. There's no uncertainty in that. We've got actual lines, right? 1.2, and then you estimate between the lines. Another way to think of this is read between the lines. So between the lines, the estimate that the author gave was 0.6 of the way. So 1.26 grams. Any questions? So here's another example, reporting the right number of digits. You use a thermometer to measure the temperature of the backyard hot tub, and you get the readings shown. Record the temperature reading to the correct number of digits. So here's our thermometer. It's in degrees Fahrenheit. We look at this, and this is 100 degrees. This is 110. They didn't write 110. They just put the 10 because to save some space, I think. So here's 100. Here's 110. And so these smallest lines represent how much? 1 degree Fahrenheit. So that means that we need to estimate the next decimal place to the tenths. So we're going to look at the mercury in here, and this is 100, 101, 102, 103. It's between 103 and 104. So it's 103 point something. All those digits are certain. We need one estimated digit. So we look at that and we think, that looks like about 4. So 103.4 degrees Fahrenheit. Any questions? So because measurements have uncertainty, and then when we do calculations with measurements, our calculators can give us all kinds of crazy numbers. We have a method of keeping track of the uncertainty in a number called significant figures. Significant figures are important because they help us to write numbers with the correct amount of precision. It's not ultimately the best way of keeping track, but it's the most straightforward, the simplest method. And students tend to find it confusing, but the alternative is differential calculus. And I don't think anybody here wants to do that. I learned how to do it when I was in college and promptly forgot. I could learn it again, but I don't want to. So we'll stick with sig figs. So in a measurement, all of the non-placeholding digits are considered significant figures. So that's the overriding principle, but we'll have some individual rules to help us interpret that. So all non-zero digits are significant. So we're looking for non-placeholding digits. Placeholding digits are zeros. They could come at the beginning of or the end. So if you see numbers that are not zero, those are always going to be significant. So the examples here, we have a 1 and a 5 there, and we have 2 1s here. Those are non-zero. Those are definitely significant figures. And then the rest of this deals with what do we do with the zeros? There's 3 kinds of zeros. So interior zeros are zeros that are between 2 other digits. So like this one, this 0 is between a 4 and a 2. This 0 is between the 2 and the 8. This 0 is between 5 and 1. They're stuck between non-zero digits. Those are always going to be significant. They're never going to be placeholding. Then we have trailing zeros. These come at the end of a number. So if there's a decimal point written, not imagined, not implied, but actually written, then the trailing zeros are significant. So here we have 5.10. So this 0 is at the end of the number. It's a trailing 0, but there's a decimal point written here. And so that makes all the trailing zeros significant. That's a trailing 0, and here we have 3 trailing zeros. These are all significant because there's a decimal point. They are not holding the decimal point. The decimal point is actually written in there, so they're not placeholders. What if it's just an implied decimal point? So trailing zeros before an implied decimal point are ambiguous. We're not sure. So this number, 50,000, there's no written decimal point. Does this mean that this was measured to the nearest 1 or to the nearest 1,000, or is there uncertainty maybe in the 10,000s? We can't tell. So we want to avoid using that. So here are the ones covered, by this example. Those are trailing zeros with an ambiguous definition, an implied decimal point, and the 0 and the 10. So if push comes to shove and you have to identify these, we're going to go with the worst case scenario and say they're not significant, but it's hard to tell. So as an example here, 350. That might have 2 significant figures or 3 significant figures. We often abbreviate significant figures as sig figs because significant figures is really long. If we put this number in scientific notation, it gets rid of the ambiguity and the confusion. So if we mean that the uncertainty is in the 5, there's 2 significant figures, and this 0 is just holding the place, we would write this as 3.5 times 10 to the 2. If we mean that, no, this was measured to the nearest 1, then we could write this as 3.50 times 10 to the 2, and that has 3 significant figures. That tells us that the uncertainty is in this last digit. Here the uncertainty is in the 5. So when we write a number in scientific notation, all the trailing zeros are significant, because there's a written decimal point. If there's going to be some zeros, there's going to be a decimal point. Leading zeros are the zeros that come at the beginning of the number, and they are not significant. They are only there to locate the decimal point. So this number, 0.0005, these zeros, their only purpose is to hold places. If we didn't have those there, it looked like 5, but this is actually 0.0005. It's much smaller. And here, this 0.0153. Those zeros disappear when we put these numbers into scientific notation. Any questions? There are also exact numbers, and these can arise from 3 different sources. Exact counting of discrete objects. So like when we counted the 7 pennies in the picture, we're counting discrete objects, and there's no uncertainty at all. It's exactly 7 pennies. So that can happen. We can also have integral numbers that are part of an equation. An example of this would be that the diameter of a circle is twice the radius. The diameter is exactly twice the radius. There's no uncertainty in that number. So this is an integer, a whole number that's part of an equation that's exact. And then we also have some defined quantities. An example of a defined quantity would be that 1 foot is equal to 12 inches. A foot is exactly 12 inches because we defined it that way. Okay? So this is a conversion factor, a relationship between 2 different units that is an exact number, a defined quantity. Other conversion factors are not defined quantities. So some are, some aren't. So let's practice counting sig figs. So in this first number, 58.31, how many significant figures are there? 4. Because there aren't any zeros. It's easy if there are no zeros. Just count how many digits are there. It's when we get into zeros that we have trouble. Okay, so this one, 0.00250. 3. This one has 2 different kinds of zeros. It's got the leading zeros. Those are just holding decimal places. And then we've got this trailing 0. We're going to count the trailing 0 as a significant figure because there's a decimal point here. This 0 isn't holding a decimal place. It's giving us information. So we're going to count the 2, the 5, and the 0. How about this one? 2.7 times 10 to the third. 2. In scientific notation, all of these digits are significant. The times 10 to the whatever, that's where the place holding comes in. So 2.7. D, 1 centimeter equals 0.01 meters. This is an exact number because it's defined. A centimeter is exactly 1/100th of a meter. So we could say that's an exact number, or it has an infinite number of significant figures. There's no uncertainty in that. How about 0.500? 3. The leading 0 doesn't count. Scientists always put a 0 before a decimal point to draw attention to the decimal point. So that one's there just to draw attention. The zeros at the end, those are trailing zeros. There's a written decimal point, so we're going to count them. So that has 3 sig figs. How about 2,100? I would say 2. There are 4 digits there, and those zeros are ambiguous. So we're going to assume the worst, that way that we're not disappointed later. So 2,100, we'd say, has 2 sig figs. It's ambiguous. We should really write that number in scientific notation, 2.1 times 10 to the third. If these are significant zeros, we could write 2.1 0 times 10 to the third. And that tells everyone very clearly those zeros have significance. Sometimes you'll see a number written like this, 2100 with a decimal point. And you're like, that's kind of weird. Why put a decimal point there? Well, that makes those trailing zeros significant. So this is sometimes used. You might see this in worksheets or labs. The book tries to avoid using that, and I'll try to avoid using it in lecture as well, but just know that that exists. So if you write it that way, it would have 4. So it has 4 sig figs. This one has 2, and this one has 4. Any questions?